imbalanced class problem in machine learning.
Thank you, Pratik. And good afternoon to all of you. Am I audible?
Yes, sir.
Okay. No, I think is it visible?
Yes, sir.
So, good afternoon. Today we have take a session on handling imbalanced data set in a machine learning problem, or basically it is saying imbalance classes problem in a machine learning. So before we start with the imbalanced data set, but first we have take a scenario on a machine learning problems. Just we can say that our data. So that is data. I think it is a image data, signal data, tabular data. So first thing we have a data. Then this data it is taken X and Y. I think everyone is knows X is a number of columns and Y is the target values, and it is passes into a ML model. So and we have to predict the value of Y. And after that, we have to predicting the value of Y, or we can say that Y hat. So this is the correct levels or not. So in that case, we have checked that accuracy problem. So we have checked accuracy. So this is the traditional machine learning problem. If a data means either signal, image, or tabular data, numerical text data, any kind of data we have to pass into a ML model. In between data and ML, we have a pre-processing task. We have a skipping here. Just we have a data and pass into ML model, and we have calculate or find out the value of Y, and it is a binary. Basically, I have taken a binary class problem. So it is a binary class, means either 0 or 1. So in that case, we find that accuracy, assume that it is 99%. So it is basically a traditional machine learning problem. So if we find the accuracy is 99%, then we can say that that model is good. But in imbalanced data set says, if I just to take an example, so we have taken example of the cancer data of a trained model in a cancer data of image data. We have taken a DL and ML algorithm, then the accuracy is find out that 99%. But just scenario, we have checked that it's confusion matrix. So these confusion matrix is misses all about the positive examples. So sometimes misses that positive example, and then so this one. So looking at the confusion matrix and model misses the positive examples, means most of the models is classes belongs to, or data set belongs to a true negative or false negative and false positive, or confusion matrix says it is belongs to a misses all positive samples, that is we have taken or we have find out exact, means if a model have a cancer, then we found out either this assume that it is 0 and 1, and this is no cancer, and this is a cancer model, then we can say that these one samples are misses most of the time, and it is predicting no cancer. Then this type of problem is called as imbalanced classes problem. We have a problem class which is not properly balanced. Means either one of the classes is minority and one of the classes is majority. So in that case, we have overall error is biased towards the majority classes, and majority classes, in that cases we have not the correct solutions. So just like that, we have had some training negative example, we have two positive example, and then model is biased towards the negative samples, but we find out the positive samples. So in that cases, the model is not good, and then accuracy is not good for saying a particular model is good or not. So that problem or that data set is imbalanced. So basically we can say that a model, a machine learning model, and passes into and data, and when find out result or class, and in that cases we find out that accuracy and assume that it is 99%. So but imbalanced cases, that 99% classes or accuracies belongs to a majority of classes, and then zero class is assume that it is 100 sample, it is 200 sample. So it is 200 sample, and 0 is belongs to 150 samples, and 1 is belongs to 50 samples. So the output or accuracy or model towards bias to the 0 class samples. So this is imbalanced data or imbalanced class of problems. So, and then problem for the imbalancing. The problem for learning of imbalanced data is basically to handle imbalancing in a data, or we have a correct model for machine learning model for a particular type of problems. So we have some issues in machine learning problems. So first thing is a class distribution is skewed, and when the data has an underrepresented data, or it is high level of accuracy is simply misleading. So in imbalanced type of problem, imbalanced learning or imbalanced class problem, we cannot says that accuracy is 99% and model is 100% or accurate or more robust. So in that case, accuracy is not a measurement of particular model is good or not. So first thing, we have to split some, switch to some other accuracy or some other matrices, just like F1 score, precision, and recall. So in imbalanced data set, just we have basically focused on two matrices, that is F1 score and recall. So the class distribution is skewed, and means it is towards a model towards a particular type of class, means majority of a class, either it is 0 or 1, means either it is a particular want a particular decision yes or no. So it is towards a particular majority of a class. Second thing, it is a high level of accuracy simply is misleading. So we cannot focus on accuracy. So we move some other matrices like F1 score, precision, and recall. So for that kind of data, we have a simple some approaches to handle imbalanced class of problem. So we have 5 or 6 problems. So first thing, it is a undersampling. So we have to undersample to a majority of class. So so just a random undersampling, we have one example of that. Random undersampling, it is a balance the distribution by the randomly eliminate the majority of examples or majority of a class. Let us take an example here. Just this is a data set and class distribution, and this class distribution is about 900 times, and this class distribution is about 100 samples. So the machine learning or undersampling says we have to take a random sample from a majority of a class, and rest of the samples are removed, and then we pick just a 100 sample from that class, and it is zero class, assume that, and it is one class. So, and one class it is simply 100. Then these two samples are picking for, we have to ML model and pass into a ML model these two samples, and then find out the class, or we have to model on that. So just undersamples says, just we have take a randomly picked 100 samples, because of it is 100, so we have to balance it 50-50%. So we have picked 100 samples from 900 samples from a zero class, and then it is 100 class, and these two samples passes into a ML model and find that particular problem into a machine learning problem. So in that case, we have not find out the accuracy. In that case, we have calculate F1 score and recall and precision. Okay, so this is the undersample the majority of classes. So this is the one drawback of that, that is a loss of information. Because of that, we have removed 800 samples from a zero class. So it is a loss of information, and this is not a good approach for handling a imbalanced class of problem. Second thing, in that second example, this is oversampling the minority class. We have to upsamples or oversample the minority of a class. So again, we have take the same example. So it is 100 sample and it is 900 samples, and it is belongs to class 1, and this is belongs to class 0. So the upsample is just a duplicate of this sample into equivalent to that. So in that case, in that example, we have to duplicate 1000 transaction in 9 times. So the sample is like that. So it is 900 times, and this one is belongs to different class. Again, it is a 900 times. It is 0 and it is 1. And these two data set or values passes into a ML model. So this oversampling of the minority class, we have to, minority class means it is class 1 here. So we have to upsamples this class into equivalent to a majority of class. So the advantage of that is no information loss. We have, and second one, the disadvantage is it is overfitting. So it tends to be overfit a model. So we have oversampling. So these two, undersampling and oversampling, it is having a problem. First one, undersampling is information loss, and second one, oversampling is a overfitting problem. So it is, these two are the naive application, naive approach. So we have not used regularly. So, and oversampling and undersampling. Second one, it is synthetic data generation, or we can say that we have to oversample. So this is oversample the minority class using a KNN algorithm. So this is called as ISTE analysis. Sorry, ISTE techniques, a synthetic minority of a class oversampling techniques. So it is generating samples of a minority class. And here it is using the KNN algorithm, means it uses a nearest neighbor algorithm. So that again, ISTE is overcome the problem of information loss and overcome the problem of overfitting. So this is example of that. That is blue circles. It is a more than the squared red square. So we have to oversample. We have to oversample this orange squared into a equivalent to a blue circle. So in that case, we have to generate a synthetic data set and using that nearest neighbor algorithms. So in that cases, we have to generate one samples using 1, 2, 3, and 4 neighbors. So in that cases, we have using 4 neighbors. So for that algorithm, we have picking 1, 2, 3, and 4. So every one synthetic data generation, we have to use 4 neighbors. And this is the equivalent of data. means equivalency of the class blue and then class red. So this is most of the time this concepts or this methodology are using over the undersampling and oversampling. So this is the synthetic generation of a minority class using oversampling techniques, that is called smooth analysis, and it uses the k nearest neighbor KNN algorithms. And this is mostly used in case of these three techniques: undersamples, oversamples, and smooth analysis. These one are using the before passing the data into a model, and this is cost sensitive approach. This is exact done during the training time or model generations. So in that cases, cost sensitive techniques. So this is the this one. This is the class label, it is weight, and class weight is a balance. This is the two fundamental keywords are using in a cost sensitive approach. So basically in that cases, we have a data set, and this data set is passed into directly in a machine learning algorithm, and it is a specific kind of ML algorithm. It is not applies on a particular kind of problem. So ML is basically having a tree kind algo. In that cases, we are using a tree kind algo, and we have to calculate the value of y or this. So the tree kind algo it is a class weight is one parameter, it is a class weight is a balanced, and class label is a weight. So in that special kind of algorithm, it is a decision tree. In that cases, we have using a random forest, and in that cases we are using the XGBoost. If that using a gradient boosting tree, and it is some tree kind of algorithms. So the cost sensitive, we have approach during the training time, not before applying, or in that cases here in a pre-processing time. And these three algorithms are before the ML training or before the training. So this is in a pre-processing time. So these three algorithms are done before the training, and these cost sensitive are done during the training time. Means this like a decision tree approach or a tree kind of algorithms. So same here. So this is same in previous one. I think I have written one SK. I think we have repeat these two slides. So we have four or five kind of approaches to handling the data set. First is that is the undersample. So this is undersample. This is the problem having a loss of information. And second one, we have to approach oversample, and it is disadvantage is a overfitting, tends to overfit a data, and we have to remove these two overcomes using the smooth analysis. And fourth one, and these three are done in a pre-processing step. And last one, it is a tree approach or I think cost sensitive, and this is done during training. So this is some theoretical points to handle a particular problem is imbalanced or not. So we have some hands-on on these kind of problem, how to solve that kind of problem using a particular in a Python programming language. So I think we have to move some hands-on sessions, hands-on. So anyone, anyone having any problem, questions in theoretical point of view? Next, we have to implement these algorithm in some specific data, that is diabetes data, and it is downloaded from the UCI repositories. That is PIAMA diabetics dataset. Anyone having any issue and any questions? So can I move to the hands-on session? So I think move to the hands-on session. Our screen is visible.
Yes, it is visible.
So how to handle these kind of problems, imbalanced class problem in Python. So in Python we have a specific library that is called as IMBlearn for that imbalanced dataset problem. So this is the IMBlearn for that data imbalanced class of problem. Okay, so first thing to install that, just we have to use for installing that IMBlearn, we have using a pip, just pip install imbalanced learn. So just we have to use, that is pip pip, and install the imbalanced learn, and that it is installation. Okay, so for installation, that for imbalanced class of problem, you are using a imbalanced learn library, and first thing we have to import in IMBlearn, and in that complete hands-on session we are using the XGBoost classifier, and we have to compare different kind XGBoost classifier in for a different kind of imbalanced handling imbalanced kind algorithms, just like smooth and undersample, oversample, and compared to a output means F1 score to different approaches. So first thing, we have to import all these libraries. Second one thing, I have using a data set that is the diabetes, and it is a PIAMA diabetes data sets. So just import that data set, and it is about 8 columns and 768 rows. So it is 768 examples training sets, and it is 8 columns, sorry, 1 2 3 4 8 9 columns, and one is a target value, and in that cases outcome belongs to a target class, a target value. So the output distribution means the column distribution or classes distribution. It is 500 belongs to a 0, means a particular person having without diabetic, and one class belongs to, means one is belongs to a diabetic. So it is 268. So in that cases, just we have see there have. So class 1 is belongs to 268 samples, and class 0 belongs to 500 samples. So about it is just a double. So this is not a equal and approximate equal. So that is imbalanced data set. So we have just plot that is diabetic and non-diabetic. So we have a non-diabetic, it is a 500 samples, and diabetic, it is a 268 samples. So this is distribution of a class. So we have to split our data set into X and Y, the training label data in X and Y. So just we have to, and important term is here, in any machine learning problem and any concept of removing imbalanced data set, first thing we have to split our data set. Then a data set having a train and test, I think we have written here, train and test, and we just pass the train data set into a approach, imbalanced class approach, not the whole data sets. Okay, so this is the important term. So we have to distribute or split our data sets, and just we have to percentage, means 65% to class 1 and 34% to class, 65% to class 0 and 34% to class 1. And it is a XGBoost classifier. So we have passed the X and Y data set, then it is the X train and Y train. We have split our data set into 30-70 ratio, means 70% belongs to a train set and 30% belongs to a test set, and same for the Y. And we have to apply a model, that is a XGBoost classifier, and it is some parameters or param values or parameter values, and it is a binary, that is a logistic type of binary classification. And in that cases we are using a gradient boosting tree, and learning rate is 0.1 and maximum depth is 4. So it may be not a specific value, just we have put a randomly values. Okay, so you can set a different values here. So according to that param, the output is different, means the accuracy and some other things are different. So we have to fit that model, and we have to predict that model, and then we have to plot that classification report, and that classification report contain a precision, recall, F1 score, and sample sizes, and etc. So just we have to simply run that algorithm. So before we are using any imbalance class algorithm, so that is we are using XGBoost classifier, and here it is a class 1 precision is 57%, and because of we need only a class 1. Class 1 means it is a particular person having a diabetic, and class 2 belongs to non-diabetic. So we are focusing into a class 1, means a person having a diabetic. So the precision here, class 2 class precision here, the class 1 it is 57, recall is 0.72, and then F1 score is 61. And in that cases we have to support it is 81 classes belong, means 81 samples are matched to a class 1, and here in that cases 150 samples are matched to a class 0. So before we are using the imbalanced class, our model XGBoost classifier, and that bias towards a class 0. So without handling imbalanced data, that model, means our model XGBoost classifier, it is biased towards a class non-diabetic patient. So this is our normally, without applying any handling approaches, imbalanced approaches, it is generating then F1 score, precision, and recall. So again, important term, we are not focusing on accuracy, because of accuracy leads to misleading. So we are not focused accuracy in imbalanced class. Just we are focusing on ROC, AUC ROC and precision, recall and F1 score. We are using TPR, FPR. So we are not using the particular accuracy. So we have to use here the first undersample techniques. So in undersampling techniques, we have to remove a majority of the class. So in that cases, we have to remove a majority, means non-diabetic class from our data sets. So here some sampling strategies are here. So if that cases, so IMB learn, we have to import a library, that is IMB learn. In IMB learn, we have to use the undersampling techniques, and that undersampling techniques, we have used a particular function of particular techniques that is called a random undersampler. So the random undersamplers, it is just picking some strategy sampling techniques, that is 1 and 1.2. So the 1 means the equal number of class. So majority is 50%, then minority is also a 50%. Then sampling strategy is 1/2. That means the minority belongs to more than majority. So it is just a 50% and some other is a 40%. Sorry, 60% and some other is a 40%. So this is our random undersampler. So we have to apply the random our sampler, fit and resample that data sets X and Y. So this is resample. It is class 0 belongs to 500, class 1 belongs to 268, and that random undersampler remove remove the data from the majority of a class, and it is equivalent to a other class. So the class 0, it is 268 and class 1 is a 268. So just we have to percentage, and we have apply a XGBoost classifier in that cases. So here we have, just wait, we have to screenshot of for a comparing. That is one. So this one, random undersampler. So this is the normal algorithm and this is the random undersampler. The normal algorithm says the precision is 0.57, recall is 0.72 and F1 score is 0.62. So we have to apply a random undersampler, then precision is increases to 0.83 and recall is 0.71, and also F1 is also increased. Here it is 0.62 and here it is 0.77. So admin support says in that cases we have matching the sample, it is 81 and to class 1 and it is 152 to class 0. So in random undersampler, so it is matched approximate equal. So it is 80% samples are matched from 268 and it is 81% or 81 samples are matched from 268 samples. So we are using the random undersampler. So in that cases we are improve that F1 score and improve the precision. But the problem is here we have removed some data set, some data samples from a particular class, and it's generate a loss of information problem. Second one, the concept is a Tomek links. The second approach for random undersampler is a Tomek links, and again it is a part of undersampling, and then for applying we are using a Tomek links functions here. So just simple, we have a resample, we have to variable that store the Tomek link functions, and we have to Tomek link function aliasing with the fit resample, so resamples of our data set. Okay, sorry for that. In that cases, every time we have to apply after the train and test splitting. In that cases, we have to use only just data X and Y. We have not using the train and test split data. So in that cases, we have to pick train and test split data. So it is X train and Y train. So it is this one. So it is X train and here it is Y train. And then it is outcome is 313 and 157 because of we have just pick 70% of data samples. So data sample is 768 and we have to pick the 70% of that 678. So the total samples about 500 and it is 0 class belongs to 313 and 1 class belongs to 187. So the same concept is here and this AICTE-ISTE classifier now here. So in that cases, we have to compare with the previous one. So it is 75, sorry, 57, it is 72 and it is 64. Again, in that cases, it is generating more F1 score here. So it is more F1 score. It is 0.64 to 71 and here it is precision is more, and for a random undersampler the precision is 83 and F1 score is 0.77. So this is for the tomic links. And third one we have using a ENN. Again it is a neighborhood nearest neighbor algorithm, that is edited neighborhood nearest neighbor algorithm. So in that cases again we have using a particular kind of algorithm, that is the edited nearest neighbor algorithm, and again we have to use a fit resample. So here we are using train and here it is using train. So in that cases, for using Wilson EEN algorithm means edited nearest neighbor algorithms. We have to improve F1 score and precision and recall. So we have to improve these three. Precision, it is improved. It is previously it is 5.57 and it is here it is 86 and it is 88 and in that cases it is 87. Again the support value is less, it is 53 and 56. So in that cases support value of a 150 samples is 94 for class 0 and 56 for class 1. So this is the random undersampler algorithm, and these three algorithms are used, but in practically we are not using these three algorithms excepting this edited nearest neighbor algorithm, because of these three algorithms leads to loss of information. So if I using that algorithm, so we have to suffer from loss of information problem. So it may be okay. If you are using any of these algorithms, then you have to use a Wilson's EEN algorithm or edited nearest neighbor algorithms. Next is oversampling techniques. Again, if I using that oversampling techniques, we leads to the overfitting problems. So we are not using a specific or rigid oversampling techniques. So here we are using the random oversampling. So IMB learn again library for that. Oversampling is a functions our package, and in oversampling we have using the random oversampling, and sampling strategy is 0.1. Sorry, 1. So it says the minority observation is equal to the majority, equal to. And again, and undersampling, we have the sampling strategy is 1.2, and oversampling it is less than 1. So it means a minority observation is 0.8 times more than a particular type of data. Here it is 0.8, 0.6 and 0.4. So if we are using here, it is 0.8, means we have the observation minority type of observation 0.8 times more than the majority of observation. So again, we are using after the training and testing. So again, this is random oversampler. So previously we have 268 samples, so it is moving to the equality of the exact sample. So we have the sample is about 500, so we have moved more than or equal to the minority class, sorry, majority of a class. So this is the 700 and 700. So this one, this is, so original data sample is 500 and 500. We have to split our data set and training and testing. Then it is a 350, about a 350 in a X-train. And so we have to resamples into a minority, sorry, for a particular majority kind of. So it is 350 to 350. And for we are using the XGBoost classifier in that concept. So here the precision is also improved, recall is also improved, and F1 score is also improved without using random sampler algorithm. So this is the without using random sampler algorithm. XGBoost, precision is 0.57, recall 0.72, and F1 score is 0.64. And in that cases, the class 1 is belongs or improved from without applying random undersamplers. Okay, so this is next is smooth analysis. Again, this is not using in regularly because of it tends to a overfitting problem. So this is using most of the time, that is smooth analysis, means a synthetic modification or synthetic data generation using the oversampling techniques. And it uses the nearest neighbor algorithm, and that in that cases we are using sub smooth function, and then sampling strategy is same, the equal to the majority of class. So we have to upsamples a minority class equal to a majority of class. So here it is using 0.1, means same number of class, same number of samples, and in that cases we are using nearest neighbor is 2. So it is X train and Y train. So in that cases we have to use 700, 700, and just like the previous one. And for using the smooth analysis, it is again more than improved
Sir, you are not audible. Hemant, sir?
Okay.
Yes, now you are audible.
So anyone is asking a question? Sanu, which kind of plotting are uses? So undersampler techniques, basically it is a hybrid, means some concept we are picking a random undersampler and some concept picking oversampling techniques. So we have some undersampling and oversampling hybrid approach. So it is a smooth tomic. So the tomic, this one is belongs to a undersampler techniques and smooth is belongs to a oversampler techniques. So this is a hybrid approach. Some concept of belongs to a tomic and some concept belongs to a property belongs to a smooth analysis or smooth methodology. So again, it is a IMB learn and it is a combination of these two techniques. So we have using here combine and then smooth import smooth tomic. So this is now we have to impact. Okay. So previous one in smooth analysis we have using size is 700 now. So this is in smooth analysis we have using a 350. So the lower class means the same classes belong to 350 to 350 means that this low minority class is moved to the majority of that class. But in smooth tomic techniques, we have using a 333 and 333 means some we have to remove some data samples and we have to up some data samples. Okay, and again it is randomly. So the smooth techniques and so this is the accuracy. I think this is much more improvement from the previous one. So previous one it is 8.85, 0.81 and 83 and this one is 0.85, 0.84, 0.84. So F1 score and recall is improved using the hybrid approach, that is the smooth tomic techniques. And next is smooth and EEN techniques. So again, this is a combination of random undersampler techniques, undersampler techniques and oversampling techniques. So here it is again a combine with the smooth and ENN algorithms. So it is X train and Y train. So now the samples is reduced to means first thing we have to improve, then some samples are reduced, then in that cases we have to just reduce, then applied and some improvement or upsampling. So in that cases that is a smooth EEN algorithm. So in that cases precision is more higher than above algorithm, but the lesser support. And so in that cases the precision is for class 1 it is 95, recall is 95, recall is 0.91 and F1 score is 93, and then previous one it is precision is 8.85, recall is 0.84 and F1 is 0.84. So in that case these hybrid approaches generating improve our models. Okay, so this is the approach before the modeling. So anyone having any problem or issues? Any question? No. Now, so we have one algorithm missing here. So this is the balanced random forest classifier, means we have two ensembles. So we have some ensemble approach. So we have some ensemble approaches here. So the ensemble approach says, in that cases we have library that is import IMB learn, ensemble import a particular imbalancing algorithm. So here we are using the balanced so I think we have two spelling mistake. So it is a balanced bagging classifier and balanced random forest classifier. So the ensemble algorithm, we have only a two algorithm. First one is a balanced bagging classifier. So it is using a bagging concept. And second one is a balanced random forest classifier. So we have using a balanced random forest classifier here. So just we have to apply, and we have a variable. So just apply all the properties, means fetching all the properties to balanced random classifier, and we have to fit just some algorithm we have to fit, or we have to train that X train, then Y train, and we have to calculate that F1 score and some values. So just we have calculate fit, BRFF fit. So for that we have just copy that algorithm completely here. This one. So that Y predictions and these two are then copy here. And now so we have to the prediction according to X text. Model is not presented here. So here we are using BRF. So in that case, we are using a balanced random forest classifier. So it is precision is low, same as without using, and then recall is improved, and then F1 score is also some slightly improvement. So that it is an ensemble approach of for handling imbalanced problem. So mostly this is used, but my scenario or I am using most of the time this one, smooth EEN, because of it is improved. It is improved precision, recall, and F1 score. And secondary, I am using smooth time. Important thing, these algorithm depends on a particular kind of data. An important thing is here, it is not guaranteed that we are using any imbalanced algorithm, so it improves our modeling. So it is not guaranteed to improve that modeling. So if you are using this kind of algorithm, then you have to apply and check. So it is not guaranteed. It is every time improve your precision recall or F1 score. Okay, so it is not guaranteed to improvement of using that imbalanced class of problem. So I think I have done. If you have any queries, then ask. If any queries, then ask. I think no query. So if anyone having any queries, then ask.
जो कुछ लिखा दिया कुछ लिखा दिया इतनी जल्दी
I think so. No queries.
Thank you, sir. I think so. Participants are not having any queries. So thank you very much for such a nice session.